So in this video, we're going to apply the first derivative test to find the local extrema or local min-max of a rational function. So it says find the relative extrema. That means find the local min and max of the rational function x to the fourth plus 1 over x squared. I've gone ahead and graphed the function here, again, because we're going to be using calculus to find the local min and local max. We don't need the graph. The graph is here just as an aid so that we know we're not making mistakes. It kind of gives us an answer key. When I look at the graph of the function, I recognize I should be getting a local minimum right here when I get a critical value x equal -1, and I should be getting a critical value right here when x equals 1. And those both look like they're corresponding to local minimum values. I also want to recognize that the function has a vertical asymptote when x is equal to 0. So I really need to pay attention to this when I look at the rational function. I want to recognize that if I try to plug in x equal to 0, I get a division by 0, which is undefined. So the domain of f of x, which is important in terms of establishing test intervals, the domain of the function is actually from -infinity to 0, and then we have to skip plugging in 0, so union, open parentheses, and then from 0 to infinity, and we'll have to integrate this information into our construction of test intervals down here. So first we start off by finding the critical numbers. We want to find the places where the derivative is undefined or the derivative is equal to 0, because those are the potential locations of relative extrema or local or relative min-max function values. So to do that, we're going to need to calculate the derivative of f of x. We need to know when is the derivative equal to 0 or when is the derivative undefined. And there's going to be two approaches that you can take to calculating this derivative. One approach would be to work with this and use the quotient rule. The other approach would be to separate this into two fractions and write it as x to the fourth over x squared plus 1 over x squared, which would just be x squared minus plus x to the -2. So we can either take the derivative of this or the derivative of this. If you work it through both ways and you do the simplifying that needs to be done, you get the same derivative when you're done. I'm going to go ahead and just kind of suck it up and use the quotient rule, although I think using the other form is probably easier in this particular case. So if I'm using the quotient rule on this, if I didn't recognize that I could break it into two fractions and I decided to take the derivative using the quotient rule, we would need to take the derivative of the numerator, which is 4x cubed, and we would multiply that by the denominator, which is x squared, and then we would go minus the derivative of the denominator is 2x, and we would multiply that by the numerator, which is x to the fourth plus 1. And then we would need to divide that result by the square of the denominator. So x squared squared would be x to the fourth. And then I want to do a little bit of cleanup. I want to notice that 2x shows up as a factor in both terms that are separated by the minus sign. So a good move would be to factor a 2x off. If I factor a 2x off of this first term, I'll get a 2x to the fourth left behind. So x times x to the fourth is the x to the fifth I'd get here, and 2 times 2 is my 4. And then minus, if I factor off the 2x, I just need to distribute the minus sign into the parentheses. So I'd get minus x to the fourth, and then minus a 1. And this is all over my x to the fourth. And as long as x isn't equal to 0, which it actually can't be because the domain of f of x is excluding 0. As long as x isn't equal to 0, I can simplify x over x to the fourth. It's just going to become over x cubed. And I'm going to get 2 times 2x to the fourth minus x to the fourth minus 1. So the critical values are going to occur when the derivative is equal to 0, which happens when the numerator is equal to 0, or when the derivative is undefined, which would happen when x is equal to 0. So usually I would get a critical number here at x equals 0 because the denominator is undefined at x equal to 0, but because the domain of f of x doesn't include 0, x equals 0 will not be a critical number in this case. If 0 were included in the domain of f of x, then x equal to 0 would be a critical number. So I'm only going to need to worry about when is the derivative equal to 0 to get my critical numbers. And the derivative will only be equal to 0 if the numerator is equal to 0. And the only way for the numerator here to equal 0 is if x to the fourth power minus 1 is equal to 0, which means x to the fourth power needs to equal 1, or x needs to equal plus or minus the fourth root of 1, and we're only working with the real roots. So this is going to be plus or minus 1, and then we look over at the graph, and that looks like, yep, that's exactly what's showing up on the graph. We have critical values -1. There's a function output f of -1. Looks like it's going to be a local minimum, and when the critical value is 1, it looks like f of 1 is going to give us a local maximum right here. So there's our critical values. So I'm going to slot my critical numbers in like we've been doing in previous videos. One's going to go here, and the other's going to go here. Had x equals 0 been a critical number, I would have slotted it in right here. But I am still going to need to use the 0 as part of the test interval process. So here's the critical numbers. These are the potential candidates for local min and local max. We need to set up the test intervals. So starting with the domain of my function, I see that it goes from -infinity to 0. So I'm going to run from -infinity to my first critical number, -1, which occurs before 0. So my first test interval is from -infinity to -1. My second test interval will pick up at -1, but will run to 0 because the domain of my function ends at 0 and then picks up again at 0. So from 0 here, now running to the critical number of 1, and then from the critical number of 1 running out to infinity, which is part of the domain of my function. So there's my 4 test intervals. And remember, now the test value is we need to plug in numbers, any number we want within the interval, and determine what the sign of the derivative is. So for example, x equal -2 is in the interval from -infinity to -1. So I could take and evaluate f prime at -2, which just means I need to plug -2 into the derivative right here. So doing that, I get 2 times -2 to the fourth power minus 1 all over x cubed, so it'll be -2 cubed. So I'm going to get 2 times -2 to the fourth power is going to be 16 minus 1 is 15. And this is going to be -2 cubed is -8. So this is going to simplify to -15 over 4. And I see that my derivative is negative. So on the left side of my critical value -1, I have tangent line slopes that are negative. And remember, the key is if we have a relative minimum, the tangent line slopes need to switch from negative to positive, and that's what tells me if I have a minimum or not. So I need a test value in the next open interval. So it looks like x equal to -1/2 is in that interval. So any number in the interval works. You try to pick the easiest ones you can. So we're going to evaluate f prime at -1/2, which means we're going to plug, we've got 2 times -1/2 to the fourth power minus the 1 over negative 1/2 cubed. So maybe I'll work this one down this way a little bit. So we're going to get 2 times negative 1/2 to the 4th power is going to be 1/16 minus 1 divided by negative 1/2 to the 3rd power is going to be negative 1/8. So this is going to equal 1/16 minus 1 is going to be 15/16. So you have 2 times 15/16 divided by negative 1/8. 2 is going to go in there 8 times, and the 8s are both in the denominator positions. So we're going to get, let's see, that was a negative 1/16. 1/16 minus 1/16 minus 16/16. This should be a negative 15/16. So we're going to get a negative divided by a negative is a positive, and it looks like we just get negative 15 falling out of that. Just doing a little bit of simplifying. Let's walk that through one more time. We get 2 times 1/16 minus 16/16 is negative 15/16, and it was over the negative 1/8. So we're going to get negative divided by negative is positive, and the 2 is going to go into the 16 8 times, and the 8s are both in the denominator positions, so 8 divided by 8 is 1. So we get negative 15 divided by negative 1 is positive 15. That's much better. So the derivative is positive on this interval, and you look up here and say, does that jive with the picture? Well, if I draw on any tangent line I want to the right of negative 1, looks like I get a positive slope. So the tangent line slopes are switching from negative to positive, and if they switch from negative to positive over a critical value C, we know we have a relative minimum. So the negative 1 is going to correspond to a relative minimum. And then we play the same game again. Pick, in the next test interval, pick a value of x that's in that interval. And then we're going to evaluate f prime at the 1/2, which is going to equal, plug the 1/2 in, we're going to get 2 times 1/2 to the 4th power minus 1 all over 1/2 cubed. And so the calculation is going to turn out to be the same as it was here, except the denominator will be positive instead of negative. So we're going to have a 2 times 1/16 minus 1 is still going to be negative 15/16, but now it will be divided by positive 1/8. And when we simplify, 2 goes into 16, and 8 divided by 8, we're going to wind up with a negative divided by positive is negative 15. So the derivative is going to be negative, which tells us that if we're in the interval just to the left of our critical value and we draw in a tangent line, a cruddy tangent line, it will have a negative slope. And then our last test, we'll pick, say, x equal to 2 is in this interval. So what's f prime of 2? Well, f prime of 2 is going to be 2 times 2 to the 4th power minus 1 all over 2 cubed, which is going to be 2 times 15 over positive 8 is just going to be 15/4, which is positive. So that tells us as we step across our critical value and we look at the tangent line slopes, they're positive. So we're again switching from a negative to positive slope. And when the slope switches from negative to positive, we're at a minimum. So x equal to 1 corresponds to a local minimum. So the conclusion we would draw from this, if we had space to write it out, and we should write it out, is that we will get local minimums at x equal to, there are local minima, oh my word, there are local minima at x equals plus or minus 1. So that's going to be the x location of those minima, And then if we want to know the minimum value, we have to plug the -1 and the +1 into the function to get the actual local minimum output. And we would need to also evaluate it if we wanted the location of the minima. So we'd have to plug that ±1 into the original function. And notice if you plug, so just as an aside, if you plug ±1 in there, so let's say we did f ±1 and dump it into the function, we've got a ±1 to the 4th power plus 1 over ±1 squared. Well, because we've got a 4th power and a squaring, the 4th power and the squaring are going to kill the negative. So we're going to wind up with just a 1 plus 1 over ±1 squared is just 1. We wind up getting 2 over 1 is just 2. And it looks like that's what the graph is showing us we should get at the output. So I could say that the local minimum output is a 2 located at ±1, 2.